Thanks everyone for joining. We have a very special guest today. Zhenfei is gonna teach us about HyperPlonk today. So we did Plonk a couple weeks ago and custom gates and all these things, and HyperPlonk is a builds on top of Plonk and is a variation on it. And yeah, very excited to learn about it today. So welcome, Zhenfei. Thanks for your time.
Sure. Thanks for having me. Let me enable screen sharing. Everybody see my screen?
Yep.
Yeah.
All right. I'm going to turn off my camera. To be fair, I can't see you, so you can see me. I'm going to talk about HyperPlonk today. So it's a joint work with me, Benedict, and Dan. The paper is out on ePrint, so check us out. Oops. Yeah, so just to set up the stage, so this talk will be about how can you build a HyperPlonk with a KTH commitment. Since our paper out, there were already a lot of talks, I mean, at least a few that are listed here. So if you want a more deep dive in any of the specific topics, say the lookup gate or the other PCS commitment, please check out those YouTube videos. They have a because the HyperPlonk itself is really a huge construction, or it has many building blocks, and it's kind of hard to cover everything within one talk. So feel free to check the other talks. Specifically, if you want to look at how we build the lookup tables, the talk number 3 is focused on that part. All right, let's move on. So before I start, I just want to give a little bit, touch a little bit on the Plonk and R1CS. Oops, I missed a C here. So R1CS. So as you guys already know, so there are like 2 types of arithmetizations in the literature or in the industry. You can write either a R1CS, for which you can invoke, say, a Grok16 or Nova proof, or you can write a Plonkish. And for that, you have a Halo 2, you have a Jellyfish, you have ZK Garage, and now you have HyperPlonk. So, so which one do you want to use then? So here we just give a study or a survey of existing implementation or useful applications. So if you look at hash functions, we look at the proof of knowledge of the exponent, which is a typical example for signatures. We look at the Zcash circuit. And also we look at, say, Zexy. Zexy is a zero execution for the, or it's a 2-chain recursion that allows you to build private smart contract. And we'll also look at the rollups for, say, 50-ish private transaction. And the last one would be the EVM circuit. So we have got some data points here. So as you can see that, the Plonk circuit is much better than R1CS. At the minimum, you will be able to get a 2x, and for large applications, you can get a 5x. You can get a 30x improvement. And I should say that the time recorded here for HyperPlonk, we should just take it with a little bit, I guess, caution. We are working on actually even faster version of HyperPlonk, and Binny told me that he was able to improve the things by another 2x. So the time here, we'll update the paper, and we will have better results here. But I want to highlight is actually the number of constraints for the Plonk and number of constraints for the R1CS. So that table itself is pretty self-explaining of why we want to use Plonk, right? And for Plonk, so what is a Plonk arithmetization? So if you were here 2 or 3 weeks ago, you has already talked about this. So it's a you can view it as a matrix, right? So you have the matrix where you have selectors or advice, and you have the witness. You put the witness here, you put the selectors here, and then you constrain that. Okay, this line of the elements satisfy certain kind of the customer gate. So in practice, you usually have, I say, a very tall table, so maybe like 2 to the power 20 to the power 30, and a few thousand columns at a maximum. And the secret sauce of having a custom gate, or the Planckish, the secret of Planckish arithmetization is this custom gate. So here I'm giving you an example of the custom gate that is building the jellyfish. So the gate looks a little bit complex, but what essentially I did is say here we have a linear combination, here we have a x to the power 5 gate, and here we have a some kind of a quadratic gate, and last one would be a quad gate. So with this gate, we are able to do say a Poseidon or a rescue S box within a single constraint. S box in a single constraint, whereas if you do it in R1CS, you need for perhaps 5 constraints also. And for the EC group additions, we are able to do additions in 2 constraints, one for the X coordinate and one for the Y coordinate. This is on the twisted word curve. Well, in comparison, in our own CS board, we need 12 to 15 constraints to do the same thing. And the last typical example that I've shown already is the Zexy versus very Zexy. So we are able to reduce the circuit, the recursive circuit by 2 to the power 5. So roughly 30x smaller circuit. That's one reason that we want to use Plonk. The other reason is the lookup tables. So if you are working on the non-native field, like a lot of ZK EVMs, then you are going to use range proofs to constrain the native field. Non-native field is actually within say a certain lim. So you rely heavily on the range proofs, and you can also use the lookup argument for P-pingers, where P-pingers has a window, and you can just use that is a lookup for the window. So amortized cost for a group operation would be 300 constraints if you use lookup tables. So those are all the good things why you want to use Plonk. And in industry, we'll actually see that everybody's using Plonk. I mean, really, we see a new project that is spinning off on the R1CS now. So the question next would be, what is a Plonk, right? So, hang on a second, sorry. What is a Plonk? So Plonk has, what is a Plonk library? You probably have 3 components: a front end. So in the Halo 2, you have a layouter. In Jellyfish, we have our own front end, and perhaps in RPOS, you have our own CS front end, but that's not Plonk. Then you have a polynomial community scheme. So this can be a Fry, this can be a KZG, and different proof systems tend to have different PCS, and there are some libraries that trying to make this generic so that you can switch between different PCS. That's a really nice feature there. And the last and most important part, which is what Plonk, which was what unique to Plonk from my point of view. So that this is not. You have similar things in the R1CS, but this is where Plonk shines. It's like you can use simple a zero check and a permutation check to build a PIOP. Then that's sufficient enough to argue that the witness satisfies certain constraint. So just to be precise, so zero check is to check that okay, there's some polynomial that is 0 for the point, and this polynomial is pretty large, and you want to check it efficiently. There's also a permutation check where I check that okay, one polynomial is a permutation of another polynomial. This would be useful when you try to argue some. But when you look at the matrix before, it will be useful for you to argue okay, this element here is the same as the element here, or it's the same element here. So that allows you to do a copy constraint. So that basically is all the theoretical components of a Plonk. Now, like I was saying, so in the original Plonk, or in perhaps the Halo 2 KZG, or the ZK Garage or Jellyfish, what we all have done is like we have a univariate polynomial, we have univariate KZG, and we have a PIOP, the original PIOP from the Plonk paper. Now, what HyperPlonk does a little bit differently is that, okay, the polynomial now is a multilinear polynomial, multivariate polynomial, where we will need to use a multilinear KZG commitment, and we will need to use a different IOP, which is called sum check. Okay, and in practice, how do we build up the HyperPlonk library? Okay, we are building on top of the artbox. Okay, we have the elliptical part, which allows us to build the KZG commitment. We have the polynomial part, which allows us to build MLE multilinear extensions. And for that, we build up the non-interactive IOPs. We also have the arithmetization component that allows us to plug in either Halo 2 or Zhenfei. So all the three components comprise the HyperPlonk library. Okay, I'm going to stop here for a little bit before I go into the next step. Do we have any questions so far?
So I don't know if you'll get to this, but could you just say a word on like why we're interested in converting like the univariate polynomials to the multilinear polynomials and what advantage that gives us?
Right. I was going to say this in a bit late.
Oh, okay.
Late
Perfect.
stage.
Perfect.
In just 2 slides. Yes.
Yeah. Perfect.
Okay. Cool. Okay. No. Oh, by the way, I don't see the chart. So if there's any question on the chart, can you please just pop them? Let me know.
Sure. I'll announce them if there's anything in the chat.
Yeah. Thank you. All right. So the question was, why do we want to use multilinear extensions? So before that, let's look at what is a multilinear polynomial, right? So that we know why we want to use it. So I guess a good reading source would be the Justin Taylor's book of section 3.5. It gives a pretty good explanation what is MLE and so far so forth. But for the sake of the completeness, let's try to look at a example here. So let's define a three-dimensional MLE or multivariable polynomial. So we have a 3 variables x1, x2, x3, and this is how I define it. So it's multilinear in the sense that the degree is 1. So degree is like, say, for every different variables, you don't have a quadratic term or a larger or greater than quadratic term. And then the coefficient that I put here is just from random 1, -2, 3, -4, etc. And it has a evaluation form. The evaluation form is similar to the if you are familiar with the univariate case, it's similar to the FFT representation. So you basically evaluate the polynomial at different roots. Here the so-called roots is a little different. It's a binary decomposition of all the possible points. It's a binary representation of the possible points. So it's 0, 0, 0 up to 1, 1, 1. And for each evaluation, you get for each point, you get an evaluation. So if you evaluate this W at 0, you get the first evaluation 0. If you evaluate at 1, you get 7. So 7 is like when x3 is 1 and all the rest are x1 and x2 are 0. So you get 7, etc. So you kind of build up this table. And what's good about this table is like it actually gives you the implicit formula to recompute the W. So 0 corresponding to the when all the x1, x2, x3 are not set, right? So it's 0, 0, 0, and the last one 1, and the last one 1, 1. So you have the x1, x2, x3 are all set, and you have a coefficient 4. So basically, what it means say when I try to operate over this polynomial here, I can actually look at this array. So 0, 7, -6, 4, etc. This array, and it's those two are equivalent. So we can just simply look at a 2 to the power of n size array. So n is a number of variables, 3 here, And let's look at the array and operate on the multilinear polynomial. And why MLE? So now we know what MLE is. Why do we want it? So first, we do not need any entity anymore, right? So entity was used to convert a polynomial into its entity domain or extrapolation domain, extrapolation form. But here we implicitly store the evaluations, so we don't need to do any conversions, and therefore we are linear time now. The entity was the reason that a Plonk is not linear time. It's entity is an n log n time algorithm. So when Plonk incorporates the entity, it is not linear. So without entity, we get a better asymptotic performance. And the second and more interesting point is like MLE multiplication is almost free. So here I have just stored one polynomial as an array, right? And if I have another polynomial, I have say this is W, and I have another polynomial called V. What I do is like I store its evaluations again, and that's it. I don't need to do any operations to just do. I just need to store the two n arrays. So I don't need to actually do a polynomial multiplication here. And you may imagine that why it's useful. So in the HyperPlonk, when you need to calculate, say, the vanishing polynomial, there's a lot of multiplications. You need to move to the extended. You need to do the FFT over the extension domain, etc. All these things can be avoided. Now, what's the challenge? So we have three components. We get three components for a Plonk, right? As I mentioned earlier, we have front end, we have PIOP, we have PCS. We can reuse the same front end, but we need new components for the second and third. So we need a new PIOP, which is HyperPlonk. We also need a PCS, and there are quite a few schemes there already. So the KTG based one, which was originally proposed, I think, if I'm not wrong, originally proposed in the revamp paper. There's Orion Plus, and there's Thrive variant in the MLE setting, and that's quite a few, and Hydrax, etc. So I guess our focus will be on the HyperPlonk PIOP. So what is a what kind of PIOP do we need here, right? Like I said earlier, in the Plonk, we need we need to check that vanishing polynomial is 0. So we need a 0 check on the polynomials. We also need to check that the copy constraints are correct. So we need to show that X and say F and G2 MLEs are the permutation of each other under certain permutation polynomial. So it's called permutation check. And the way we build it is say we start from the sum check, and the sum check we are able to build a 0 check protocol. And then the next step would be like instantiate a product check. I'll explain the terminology later when we get there. We'll build a product check PIOP from the 0 check, and the last step was to achieve a permutation check from the product check. And obviously the HyperPlonk will rely on the permutation and 0 check. And that once we have those two, we have basically all the PIOP that you need in a HyperPlonk protocol. I'm going to stop again just to see if there's questions, because next step would be on the sum checks. And
so yeah, I had a couple questions on the previous slides on when you were talking about like just multilinear polynomials. Yeah, like so you can do the same thing with like univariate polynomials here, right? Like you can represent a degree n polynomial with like n+1 evaluations, and then like you can represent it using like a Lagrange basis, like kind of like we're doing here.
Yes.
So, like I guess like what's the difference between doing this. Here we're doing like the evaluations times some formula. There we're also doing the evaluations times some formula, right?
Right. So in the univariate case, right, you need to convert the polynomials back and forth between the integer representation and the entity representation, or the Lagrange representation that in your terminology. Right. So you need to convert it back and forth a couple of times. So when you generate the witness, they are in the evaluation domain, and you convert it back to the integer domain to the KTG, and then you convert to the entity domain over the extension field again, and then do the vanishing polynomial. And yeah, so it's a couple back and forth, and every time it's a n log n cost. And in comparison, in the MLE part, in the MLE world, as I said in this slide, you actually don't do any of these operations. It's always in the evaluation form. So in fact, you will never see this polynomial at all, right? When you extract the witness is already in this 0, 7, 6, -6, 4, etc. This form. Right. And you never need to convert it back to the actual polynomial form. And then when you do the multiplication of two MLEs, you just extend the list by another 2 to the power n, yeah, and that by another 2 to the power n, and then you get the so-called multiplication result. So basically, the multiplication is free.
So if you have two polynomials, MLE polynomials that are length n, their multiplication would be represented as a MLE in evaluation form of size 2 to the n.
Something like that. It's when you multiply two MLEs, it's not an MLE. It's so-called a virtual polynomial. But it's no longer a linear polynomial, right?
Right. Yeah. I think that's why I'm having trouble thinking about like the multiplication of two MLEs, like what that means.
Right. Yeah. I should have this slide. I didn't prepare this slide. So it's a virtual polynomial. So it's like you can think of it that there's a polynomial that is a multiplication of two multivariate polynomials. It's just you never explicitly write it out. It's still a degree 2 polynomial, and you can still write the sum check for it, or you can still run the sum check or the IOPs on it, yeah, etc. So you still have the most property here. Yeah, I'm not sure if I explained it correctly clearly. Okay, let me try to rewind a little bit. So in the univariate case, right, when you do two polynomial multiplications, you convert those two into a entity domain and do the coefficient-wise multiplications, and then convert it back to the integer domain to get the result. And you get so you increase the degree, you double the degree basically, and you do two FFTs. In the MLE world, okay, there is a sorry, let me try to reorganize. So you have two MLEs, and each one is in this evaluation form, and you just you just implicitly store those the first MLE and the second MLE, and claim that okay, the data you put here is the multiplication of those two MLEs. And later on, you run the sum check over those two MLEs. So that's why it's called virtual polynomial. It's never a real polynomial. If that makes sense.
Okay, so if we have like two polynomials in the evaluation form, the multiplication of those would just be another column where the multiplication is satisfied just on the rows.
No, there won't be a third column, right? So it's just two columns. I just put those two columns and claim, okay, this n by 2 matrix is the product of two MLEs.
Oh,
I never need to do any multiplications at all.
oh, okay. We're representing the product as just the two columns where each column is one of the arguments of the product.
Yes.
Okay. Okay.
So that's why I said that the multiplication is almost free, because you just need a storage. You don't need anything else for that.
I see. So for like two of length n, we need like 2n.
Yeah.
Okay, thank you.
All right. So let's move on. So we are okay. Sum check. This is things start to get a little bit interesting. Okay. So just again set up the stage. So what's a sum check? We have a polynomial, the one that I used in the previous example. I want to show you that the sum of this polynomial of all its evaluations in the binary domain, so is certain S. So what it means, say I evaluate W at 0, 0, 0, evaluate at 0, 0, 1, etc. up to 1, 1, 1. I have 8 evaluations. I sum them up. It's 19. And I am a prover. I want to prove this to you. Okay, the sum is 19, and obviously the easiest way to prove to you is to send you W, and then you can do the evaluations yourself. So that will be a linear cost. And our hope here is like if we can do this a little bit better than linear, then I will show you how to do that. All right, it takes a few steps. In our case, should be 3 steps because we have 3 variables here. So first step, I kind of define a new polynomial. This time it's a univariate. I call it W1, and upon a variable x1, and it's defined as follows. So you fix the first. You let the first element of W to be variable. So still x1 here, and fix the second and third variables, and basically 0, 1 and 0, 0, 0, 1, etc. And this W1 x1 is my new polynomial. It's a univariate polynomial of degree 1, right? Because everything is, because if you just put 0 and 1 if you just evaluate x2 and x3, you see that everything is linear in x. So I will have a W1x that is linear. Okay. Now I send S, as I already know, and W1x to the verifier. Verifier checks that, okay, S equal to W10 and W11. So S he has already got, W1x he has already got, he evaluated W1x 0 and 1 and check those two as same. Once he's convinced, he sends back a challenge R1. So here the verifier is already convinced that the S is a sum of 2 polynomials, but he needs to be convinced that this 2 polynomials is actually this polynomial W1x is defined correctly, right? So it's actually defined as a W. So the W1x1 is actually defined as WX1 0, WX1 01, etc. So how he does that is through the Schwarz-Zippo lemma. So you challenge a univariate polynomial at a random point. If it's a 0, you challenge 2 polynomials at a random point R1. If the evaluation is the same, then with the overwhelming probability, the 2 polynomials are the same. So the prover needs to prove additionally that W1 evaluated at R1 random point is the same as this. And I will show you that how do you do that. I mean, actually, this proof will be deferred to the next round. Okay. So now we are moving to the next step. Next step, as you can imagine, is very similar. Okay. Now I define a new univariate polynomial W2x2. So now I have already fixed R1, right? I have already fixed R1 in my previous step. I have 1 variable x2, and I let the third variable to be either 0 and 1. I put the sum of them as before. And now I send S1 and W2 x2. I should say that actually I didn't. I think the slide missed this point where the S1 is actually W2 0 and W2. I should put it here. So the prover calculate the S1 and calculate the polynomial, univariate polynomial W2, and send those two to verifier checks. Similarly, so check that it's actually a sum, and then now he generates a challenge, and the challenge will let the prover to prove that those two polynomials are the same. Okay. Step 2, and the last, as you can imagine, the last step would be, doing it again for the third variable. Okay, so the third variable will allow you to do the same thing. S2 would be the again, I missed a point. I think there should be an item here. S2 should be the x3 W30 and W31. Oops. W31. Okay. So the prover sends S2 and W3x to verify checks, verify challenge here. And now you see this is the really last step, because the prover proves these two values. He just need to send the W R1 R2 R3 to the verifier. It doesn't need to rely on the next step to prove that this equation, this polynomial holds, or this equation holds. So at this stage, we have already arrived to the last step. We send the last steps evaluation W1 R2 R3 to the verifier, and the verifier will be convinced that the S is indeed the sum of all the things together. Yeah, so let's just recap what the cost or what actually did the prover do. The prover invoked the subprotocol for n rounds. At the nth round, it needs to do it receive a R1 RI, right? It receives a challenge from the transcript, but if we turn it into a non-interactive protocol, you don't actually need to do any interaction. You just sample RI from the transcript, and then you need to do a 2n-1 operations for the to actually get the polynomials, and then you send 3 elements. 3 elements here means that S is 1 element. So in each turn you have sent 1 element. You send the polynomial here. Since our polynomial has degree 1, so as I already showed. So you have a degree 1, so W1x is degree 1, W2x is degree 1, W3x is degree 1. And you need 2 points to uniquely identify this W1x. So in total you send 3 elements, and the operation will be, say, linear in number evaluation, or exponential in the number of variables, and you have 2n proof, 3n proof size. The verifier side, it's very cheap, right? Because all you need to do is to do one. So this equation is very easy. I mean, it's just one addition, and then you do a evaluation of the univariate polynomial. So you evaluate R3 at W3 and try to see if that matches what I have received. So at each round, I need to do an evaluation. So the cost will be log n. Sorry, the cost will be n. So the n would be the number of rounds here. Do we have any questions so far? Okay, that's good. SumCheck is something. SumCheck's out there for a few years, so it's good that we all have a good understanding of it, so that we can move forward. So as I said earlier, we want to build a couple of new PILPs from SumCheck. So the first one that we want to try is the zero check. What is zero check? So I have a polynomial W. I want to prove to you that W is a zero polynomial. So it's zero at any evaluations, right? Recall that in vanilla Planck we have a kind of we have this kind of a polynomial, right? It's a vanishing polynomial. We want to check that this polynomial is indeed zero. So this is how we are going to use this zero check in a HyperPlonk or in a Plonk system. So we for different custom gates, obviously we will have different formulas, but eventually we will have a very large polynomial, and we want to check that this polynomial is a zero polynomial. And the methodology we are doing is very similar to the one that used in the original Plonk. So we basically use a Schwarzschild lemma, which challenge this polynomial at a random point. Let's call it R1, R2, R3 again. We check that this polynomial is a 0 point. Is zero at a random point. Then with the overwhelming probability, this is a 0 polynomial. Now, to prove that W at R1, R2, R3 is 0, we need to invoke a sum check. We actually build a new polynomial f, and we invoke the sum check over f. Let's see how we do that. So we define a new polynomial f over polynomial over variables R1, x1, x2, x3, and it is defined as using this polynomial using this now this is just field element and times the equality polynomial of x1, x2, x3 and R1, R2, R3. Okay, this EQXY has this property, right? So the EQXY, this is explicit definition of the EQXY. So it has a property that if x equal to y, this EQX is 1. Otherwise, EQXY is 0. Okay, so then if we do a sum of this polynomial, this f, if we do a sum of this f, what we will see is that for x1, x2, x3 doesn't equal to R1, R2, R3, all these points will be 0 because EQXY is 0. So EQXY is 0, fx1, x2, x3 is 0. So the first part is 0. And the second part, fr1, r2, r3, when x1, x2, x3 equal to r1, r2, r3. So this one would be 1. So we actually have r1, r2, r3. So just to summarize, so we build this f polynomial such that this the sum of f is actually w that we want to prove. So if we run a sum check of f and show that the sum is 0, that means w is 0 at R1, R2, R3 at a random point. And then with Schwarzschild lemma, we show that w is a 0 polynomial. So the QED. So in practice, we build in practice how we do it. So we have the witness polynomial, selected polynomials. We do these multiplications with the multiplications, etc. With the MLE multiplications that I mentioned earlier to obtain this W, and then we build this f and then invoke the 0 check over f, and that is sufficient to prove that W is a 0 polynomial, and that is sufficient to prove that okay, the customer gate is actually satisfied.
I have a question about here. So the first, I have 2 questions. So the first question is like so you're saying like you need to first choose a random point, then you can encode this polynomial. Is that correct? So you can only construct this f polynomial f after you receive this randomness R.
Not really. So let's see. Actually, I think that's not. We actually don't need that, right? Because what you can do is that we have a f of 6 variables, and then let these 3 as variables and just store it like that. We don't really need to receive. Actually, wait. I need to think a little bit. I think we are fine just to receive this R later.
Okay, and then second question is like when you're in the Plonk, original Plonk, so this polynomial W, it isn't 0 at every point. It just only evaluate 0 at the root of unities. So, but here, like how do you define like so you should only see like the polynomial W should be evaluated as 0 when the x1, x2, x3 is equal to 0 or 1, right? So if it's a random value, then this polynomial W doesn't evaluate as 0 or doesn't necessarily have to be 0.
I'm not sure, right? Because the original Planck has to be a 0 polynomial, not only at W at the omega, but also at other points. Because by the way that you construct it.
Yeah, so you need to construct like it should equal to a quotient. Like you need to divide by like the define the quotient polynomial. So it says like it can be divided by the 1 minus x to the n.
Right.
And then equal to a quotient polynomial. But how do you do that in this HyperPlonk?
That isn't a root of unity in our case. So we are actually evaluating it at zeros and ones and at a binary point. So we just need W to be 0 at the 0 points. Sorry, at the binary point. Binary points. Similar.
Yeah, that's my question. Like that's my question. So if it might not be like always 0, like when the x1 to be arbitrary value, not 0 or 1 for this polynomial.
Yeah. Good question. So let's see. Okay. One way to do it is say we have R1, R2, R3 that is binary, but obviously that's not. There will be a soundness gap because it's space. The challenge space would be too small. Right.
Is it just that like, you know, the F and W are just defined over the Boolean hypercube? Like at the bottom equation, we're only considering x1, x2, x3 in the domain 0, 1 to the 3, right?
Yeah.
So like this check only applies to those points. We're not considering it over like we're not considering W over some continuous domain or something outside of the Boolean hypercube.
That's right, because the original witness and selectors are all defined over the hyperbolic cube. So we do not care about when the R1, R2, R3 are not binary. But I guess the question that Haichen's point, or what follows Haichen's point, was that if we only care about the case where R1, R2, R3 are binary, then the challenge space is just 2 to the power of n, and the Schwarz-Zipper lemma doesn't give you enough soundness. I guess that yeah, I think I need to think about it and then check it offline. Good question. All right. So let me move to the next. Also sorry. I was just going through the construction. So the yes, you need to receive R before you build F. So to the question that Haichen, to the first question from Haichen. So you need to you do need to get a challenge before you build R. Okay. Now we are doing the product check. So the definition of product check is say I have two MLEs. Now I'm not doing sum, I am doing product. I have all the different evaluations of F and G, and I want to show that the product of the evaluations for the two different MLEs are the same. In a later slide, I will show you why we need that. Okay, let's just bear with me. So let's go through this product check. So to be able to show the equivalence of two products, I need to have two new polynomials. Let's look at the first one. So the first step, build a new polynomial P. This P has 4 variables. I add another variable called 0. And because now I have another polynomial, another variable, I have some freedoms, so I can just set the first half of the first half of P's evaluations. So AKA P0, X1, X2, X3 to be the ratio between X and F and G. So precisely you evaluate F at all the points, you evaluate G at all the points, and you put the ratio of the two evaluations as a first part of the array for P. That's the first part of the P. And the second part of P, okay, I'm going to use a inductive formula here. So I want to have P1x to be Px0, x1. I will explain a little bit later why I want that, but just to give an example. So if I have P000 and P001, I want to have P110 to be equal to the product, of those two. And since I have already got P0, x1, x2, x3 I have already got this from the ratio of F and G, I will be able to compute all the rest of P where the first element is 1. So by just recursively call this formula. So basically, so if I have P11, P00001, I get P100, right? So if I have these two elements, I get this guy. I get these two elements, I get this guy. I get this guy. So essentially, you can see that this I get all the elements except for P111, for which we don't really care. We can just set P111 to be 0. And I guess the interesting part is that if I do a product of P where the first variable is set to 0, if I do a product of this, it will by how I construct it, it will be P1111, right? And I just need to set this P111 to 1. I shouldn't say I set P110 to be 1. Is that if F and G, if the product of F and G are the same, then this must be 1. All right, I will show you in the next slide. So, oops. Oh, sorry. Yeah. So I guess the key takeaway is like by construction, if F and G has the same product, then P1110 is 1. Otherwise, this would be a random value. Okay, just by this construction and you unify the two elements together, yeah, unify these two elements together, etc. You get four terms, and then you again unify those two terms, unify the second two terms, and you get your arrive here. In the end, you got to P1110. This P1110 would tell you if F and G has the same product. Now that we know this, how do we prove it? We know we've built a P that has this nice property with regard to F and G. How do we prove it? So we use a random linear combination. So we have the first part. First part, okay, is this formula, right? So 1x, x0, x1, 1x, x0, x1. So the first part is like, say, I'm showing that, okay, that constraint is satisfied. Then I have a second part. So R is a random number. So the second part would be this. I'm telling you that, okay, P at 0 x is times G is F. So if those two constraints are met, then Qx must be a 0 polynomial. So now I just invoke a 0 polynomial. I prove to you that, okay, Q is a 0 polynomial. Then I get to know that, okay, P. I get to know that, okay, this equation hold and this equation hold. additionally, I proved to you that Q1110 is 1. Then you are convinced that F and G have the same product. Are we good with this one? Okay. All right. Oops. I guess I explained it a little bit too early. I have another slide for this. So yeah, we had this Q defined as before. Just to repeat myself. So we invoke zero check on Q, and we additionally prove this one. The Q110 is 1. Then we have the then we prove those two constraints, two equations, and then that means the product between F over G is product of P0 with variables, which is P110, which is 1. So the product of two elements are the product of those two MLEs are the same. Okay, so now we're going to use product check to build a permutation check, and this is our end game. So once we have this, we have all the PIOPs. So this, I think it's a very standard method from the Planck paper. So we build A, which is a F. Just to rewind a bit, we have two polynomials F and G, and a permutation which is given as a polynomial MLE as well. So we say that okay, F and G, G is G is equal to permutation of F. So we build two polynomials A and B, and we with some random challenges beta and gamma, and we claim that okay, the product of AX and the product of BX are the same. So by the Plonk paper, I mean, you can look at it in more details. Look at the paper later. By this lemma 5.3, we know that A and B are the permutation from sigma. Okay, I'm going to skip the details here. Okay, all right. So next slide will be a PCS. So actually, I think in the interest of time, I will just quickly go through the PCS. The PCS was something already, so something in the we ran paper. So it's KZG-based commitment. Actually, I have only 7 minutes left, so let me skip this slide. So I guess the takeaway is like for the verification, we need to do say so this here is n parents and it's 3, right? N is the number of variables. We need to do n plus 2 parents for each. Yeah, for each verification. So the KZG verification is a little bit expensive. That's a key takeaway from the KZG commitment. I want to quickly jump into the performance in the interest of time. So let's see. So we look at we actually had a pie chart for different components. So around 45% of the time is spent on the MSMs and 50% of the time is spent on the MLE evaluations. This and 0 time spent on the FFTs. This is quite drastically changed from the Halo 2 or other Planck system, where 80% of the time is spent on the MSMs and say 15% is spent on the FFTs. So yeah, we think that is more hardware friendly. So the MSMs, you see that you can do it fairly efficiently from the other GPUs. There are some data there. We believe that, I mean, with better hardwares or even ASICs, you probably will be able to. And it's a map reduced problem. So you when you have a large dimension, you just break it down to the smaller ones and run it in parallel. Yeah, with better hardware, you probably will be able to do it a lot faster than what's been reported here. And MLE evaluation. So this may be new to some of us here because we are more familiar with the Univariate and NTT, etc. So basically, it's like I have a MLE in the form of 2n variables, a 2n dimensional array, right? That, as I have shown earlier, so for 3 variables, we have an array of 8 elements, and we have a point P that is 3 field elements, and I want to output a FP, which is F evaluated as P1, P2, P3. And for n equal to 20, this takes like 35 milliseconds on CPU. And for FPGA, this can be reduced to say 1 millisecond, and it becomes a bandwidth bounded problem, because the computation itself is very fast. It's like you, for every element that is sending, you just take one field modifications. So it takes actually 1 millisecond to transfer this 2 to the power 20 field elements to the hardware. But again, it's hardware friendly in a sense, like if you have more FPGAs or if you have more CPUs with higher bandwidth, you can just parallelize it perfectly. And the third part that I want to talk about hardware friendliness is witness generation. It's a little bit different from the Halo 2 or Plonk Plonk design. So on the left, we have some result from the from our benchmark on the KEVM circuit and the recursive circuit. We showed that maybe after the optimizations, we spend 50% of this 113 out of 256 out of 245. So it's roughly 50% of the time spent during the phase one, which is mostly spent on the witness generations. And this can be changed for HyperPlonk. In the HyperPlonk, we do not need to wait until all the witnesses are generated. Let me just rewind a little bit. So in Halo 2 or in the original Planck, your witnesses are in the entity domain. So you need to extract all of them together. Then you do the inverse FFT, inverse entity. You get the polynomial in the integer domain, and then you do the MSM for KZG. So that's a serial operation. So you do the FFT, you get all the witness, then you do the FFT, and then you do MSM. In the HyperPlonk, as I showed you earlier, so the polynomials is already in its evaluation form, and we never need to convert it back to the integer. So when you do the KZG commitment of them, you can just extract the first 100 witness to the MSM, and then we get the next 100 witness to the MSM, etc. So that allows you to pipeline things. So what means it's like your witness generation time is overlapped with your MSM times, and like that you amortize the witness generation time away. So that's a whole idea of and that's a third degree of the hardware friendly, which you don't actually see it on the paper, but theoretical people doesn't really care. Okay, all right. I'm at my last slide. I have 2 minutes left, so that's good. So just to give you some performance comparison between say HyperPlonk, Jellyfish Plonk, and Spartan. The Jellyfish is fast, I think. Yeah, the Jellyfish is faster than the HyperPlonk when the dimension is small, but when the dimension grows larger, HyperPlonk becomes faster. In the meantime, for Spartan is very slow to start with, but when you get to the higher dimension, it almost matches the HyperPlonk's performance. I guess one caveat here is like Spartan is written in the R1CS, and the whole point of HyperPlonk is say we want a Planck-based scheme, and we have already shown that the R1CS is like say 30x larger in terms of the constraint size. So a fair comparison would be say Spartan, maybe Spartan here 2 to the power 20 versus HyperPlonk at 10 to the 16 or 17 or 18. So plus. The other part, the other feature that I didn't touch upon is the hardware. It's what's in the HyperPlonk paper's title. It's a high degree. It's how to say it. It's very friendly to high degree gates. So here we are doing a customer gate. So the customer gate would be having a degree gate, having a degree D. So the D from 1 to say 32. So we can actually go from a very, very high degree, so W1 to the power D, and we'll only incur a additional maybe less than 20% of the cost. Whereas if you are looking at the Plonk paper, because this if you look at the original Plonk, this D influenced the extension domain. So your extension domain will be increased by log D bits. So if you are already a ZK EVM of 2 to the power 27 number of witness, and your D becomes a 16, then your whole FFT domain needs to be 2 to the power 31. And just keep in mind that say BOS3 one curve doesn't allow you to go beyond 2 to the power 31. So you actually can't use anything beyond that. Whereas for the HyperPlonk, you can actually use a D that is much larger without any constraints. The last one would be the performance, multi-threading performance. Yeah, it's kind of okay, but we don't really get a linear improvement with the number of threads. So we're still working on that, I guess. It's mainly due to the fact that our underlying library is not very optimized for the multi-threading. All right, that's all for my talk. I'm happy to answer questions.
Thank you. I have a quick question. You mentioned it could improve witness generation. Does that assume that when you fill out, so my understanding was that like you can partially fill out the witness table, then like kick off the commitment computations for that partially filled out witness, and then you can like go fill out the rest of your witness table, and then once those columns are done, you can kick off the MSM for like whatever the polynomial commitment. That would be column by column, right? Like because each
no, that's a row. That's row by row. You can do row by row. You can do column by column. Doesn't really matter.
Well, but the polynomial that we're committing to corresponds to the column, right?
Yes, but
So,
we do not need to receive the whole column. I mean, you just need to receive part of it to be able to commit. To start the commit process. Let me just give you an example here. Let's go back to the example. So here we have a polynomial, right? We have 8 elements. Suppose that I only receive these 4 elements, right?
yeah.
And I can start to do MSM of these 4 elements. And the commitment would be something like this 4, the commitment, the MSM of this 4 and the MSM of this 4 and then add together, etc. But we can already start the process when I receive the first 4.
I see. So it's like, yeah, because my question was like, because the witness generation hit was filled row by row, but the commitments are column by column. So you're saying like we can do partial commitments to each column, like we could do like the sub MSM additions. I see. Okay, awesome. Thanks.
Yeah, like I was saying earlier, so for the original Plonk, you need to receive the whole row and then do the FFT and then do the MSM. So that's a bottleneck. You don't, if you're missing one element, you won't be able to do the IFFT, so you won't be able to kickstart the MSM part.
I see. That's awesome. Yeah. Anyone else have some questions? All right. Well, thank you so much for your time, Zhenfei. That was awesome. HyperPlonk is very cool.